Liying.
Oh, okay, so I will start to share my screen.
Yes.
So, all right, so good afternoon, good evening, or maybe even good morning, depending on where you are. So I will talk about the solar irradiance effect. I will talk about the solar irradiance effects on the upper atmosphere on time scales from solar flare to solar cycle. So here the upper atmosphere means the thermosphere and ionosphere. I don't know why I cannot switch step.
There are little arrows down in the left corner, lower corner of your slide. Use those.
Okay, all right, okay. All right, so so you probably all familiar with this solar spectrum. So the part of the solar spectrum that is absorbed by the upper atmosphere is this shortest part of the solar spectrum, the soft X-ray, the EUV, and the far ultraviolet. And this is also the most variable part. So here the yellow and the red is the variation from solar minimum to solar maximum. So when the solar radiation comes into the thermosphere, it ionizes the neutral particles. And in this ionization process, it converts photon energy to chemical potential energies. And this ionization, together with the subsequent chemical reactions, heats the thermosphere and also creates these ions and the electron and create the ionosphere. And there's a solar irradiance has variability on different time scales, from high cadence variability during the solar flares, and going through the solar rotational variation, solar cycle variation, and that on time scale also longer than solar cycle. So today I will talk about upper atmosphere variability due to the solar flare, and also talk about the diurnal variation, solar rotational variation, annual semi-annual variation, and the solar cycle variation. Since this morning, there's a lot of talk about solar flares, so I will put some focus on solar flare, variability driven by solar flare. And I will use both model and the data to look at these variations. So I will use the general circulation models, NCAR TIE-GCM, NCAR TIE-GCM, and LTR, which stands for LFM, TIE-GCM, and RCM. LFM is MHD magnetosphere model. RCM is a ring current model, and the TIE-GCM is the thermosphere-ionosphere model. And the solar irradiance is provided by FISM and FISM2. And we know that FISM2 is updated based on a lot of SDO data. And the data that I will use is a thermosphere mass density observed by CHAMP, and also from satellite drag data, and composition data from timed GUVI, and also total electron content data from the global GPS network. So first, solar flare. So here, this is model simulation of the thermosphere and ionosphere response to the X17 flare on October 28th, 2003. So here, this flare started at 11:50 and reached peak at 12. I think it's maybe before 12, I don't remember the exact time, but this is a model simulated the neutral temperature response to this flare. And so we see that as a function of the UT and also as function of altitude. So we see that neutral temperature respond immediately, but the peak is delayed compared to the flare peak. The delay is about 1 to 3 hours. And the flare effect in the thermosphere lasts for much longer, long after the flare decayed. So it's about a day. And this is a model simulation of the electron density response. So again, the electron density also responds immediately. And in the E region, it is very much driven by the solar flare. When it flare decay, it also the enhancement also goes away. This is because the E region is in photochemical equilibrium. So that's why it is so highly correlated with solar flare. But in the F region, the F region electron density is not only driven by photochemical process, it is also determined by the plasma transport process. So in the F region, the flare effect lasts longer time. Probably here is about 6 to 7 hours after the flare decayed. And this is observed and simulated total electron content enhancement to this X17 flare. Yeah, so the before flare, the flare is 11 UT. Flare peak is at 1110. So on the left is a GPS from GPS. So this is a before flare at the flare peak, and this is a difference. And on the right is a time GCM simulation. So we see that the TEC enhancement is about 20, from the GPS is about 20 TEC unit. This is more than 20% of enhancement to this flare. And this is model also. Model TEC enhancement is slightly lower than the data. It's about 15 TEC unit. And this is a model simulation of the vertical drift response to the flare. So to a more recent flare, it's X8.2 flare in September 10th, 2017. So the vertical drift response immediately, and then when flare decayed, also decay. So the decrease of the vertical drift is about 20% to this flare. And when we know that this this upward drift that is perpendicular to the magnetic field line is the mechanism that drives the equatorial ionization anomaly. So when flare happen, when this upward drift weaken, then you will see the EIA crest, the two crests will move together, and also the electron density will decrease. And this effect is observed by the CHAMP satellite. And so the flare effect is not only directly happen in the thermosphere and ionosphere, it also feed back into the magnetosphere. So here on the left here, this is a field aligned current from Ampere. So this is a left column is the data. And this is a model simulation, the simulation by the whole geospace model, the LTR model. And on the right, this column is the Peterson conductance from the model simulation. So this is a response to the X9.3 flare on September, I'm sorry, this is September 6, 2017. And so let's look at the conductance first. This is before the flare, and this is at flare peak, and this is the difference. So the Peterson conductance increased about 100% in response to this flare. And when the conductance increase, it will increase the field aligned current. So you can see the increase of the field aligned current, and when this feedback into the magnetosphere, it will change the magnetosphere ion convection, as we can see in the next slide. So this is observation from a CMOS satellite, CMOS A and E. At the time they happen to be going through the magnetosphere, the region where there's a flare response. So here, this is the flare happened about around here. So we can see that it changed the magnetic field, it changed the density, plasma density in the magnetosphere, and changed the velocity, and then changes energy. So and when the convection change, it will change the particle precipitation, the auroral particle precipitation, and also the cross cap potential in the ionosphere. So you can see this thermosphere, ionosphere, magnetosphere are all connected. Flare effect can reach in all this geospace. And the flare effect, the geo-effectiveness of the flare is greatly affected by the flare location on the sun. So here shows the X17 flare on October 28, 2003. And this is the X28 flare. This is 1 week later, it rotating to on the limb. This is the lower figure is the mass density observed by the CHAMP. So we see the mass density in response to this X17 flare is actually larger. It's about 30–40% mass density enhancement. So this is the observation. This is the time to see observed enhancement during these two flare. So the gray is X28 and the black is X17. So we see that in the wavelengths that is less than about 27 nanometer. In the XUV part, the enhancement is larger for the X28 flare. This is because this part of the solar irradiance is optically thin through the solar atmosphere, so the location doesn't matter much. But in the EUV part, these are the irradiance mostly from chromosphere, so it's optically thick through the solar atmosphere. So the enhancement actually is larger for the X17 flare, because for the X28 it need to travel longer distance, so there is more absorption. So when you put this into this effect into the model, so this is a electron density enhancement. This is a vertical. This is it's altitude. Actually, it's the model pressure surface, and this is a UT. So you see that in the lower altitude, in the E region, that's where the XUV dominate the ionization. So you see the response is about the same. You can't really see difference. But above this altitude, where the EUV part dominates the ionization, you can see that the electron density enhancement is more than two times of the when the flare is on the limb. Now the diurnal variation. So this is a diurnal variation, of course, is driven by the presence and the absence of the solar irradiance during day and night. So here, this is a model simulation of the global average mass density at 400 kilometers. So vertical axis mass density, and this is a local time. This is a year equinox 2004. So I will talk about mass density at 400 kilometer a lot, because this is a typical altitude for the low Earth orbiting satellites. So we see that the diurnal variation in the mass density is about on the order of about 100%. And this is a model data comparison. On the top is a CHAMPS satellite observation. So we are looking at 5 days in 2007. So on the left is the ascending node. It's a daytime, 13 local time. On the right is 1 local time. So you see this day-night variation. The bottom is a TIE-GCM model simulation. So the model also simulates this day-night variation, but with at day-night amplitude is less than what is observed. And now the solar rotational variation. Solar rotational variations because of the solar rotation, the 27-day rotation, so changes the active region on the solar disk. So here we are looking at the 2 consecutive solar rotation in 2003. The blue is February 25th, and the red is March 11th. So the lower figure is the ratio of the solar flux of these 2 spectra. So we see that in the EUV region, the solar flux difference between these 2 solar rotation is about 20%. So on the right here, this is a model simulation of global average mass density at 405 kilometers. So the dotted line is F10.7. And this is about 5 solar rotations during the year 2003. So this solid line is the mass density. So we see the mass density solar rotational variation that is corresponding to this solar rotational variation in the F10.7. And here in this high solar activity year, the solar rotational variation in mass density is on the order of 100%. And this solar rotation magnitude changes with solar activity. So here we are looking at the 2003 high solar activity and the low solar activity. Looking at index F10.7 in green and AP index in pink. So during a high solar activity years, you see this shorter term variability, this 27-day and the multi-day variation. So it's the solar rotation variation has a large amplitude on a high solar activity year. But in 2008, when solar activity is very low, you can see this short-term variability is dominated by the multi-day variation in the AP index. So now when you're looking at the top, the global average mass density at 400 kilometers, the blue is the data from satellite drag. So you see the mass density is also dominated by this solar rotational variation in 2003. But during a quiet year, this short-term variability in mass density is dominated by the multi-day variation that is driven by the magnetic forcing. Now the annual and semi-annual variation. So the annual and semi-annual variation is driven by actually it's because of the solar irradiance that is received by that arrive at the Earth's upper atmosphere due to the Sun-Earth distance. So there's that cause about 7% of change in the solar irradiance at the Earth's upper atmosphere. And there's also other mechanisms that drive the annual semi-annual variation, like the internal, the large scale circulation. And also sometimes there's a semi-annual variation in magnetic activity, and also lots of the lower atmospheric forcing. So here again, this is a model simulation. And global average mass density at 400 kilometers. So we see the mass density is reach the lowest near the June solstice, and then secondary minimum is near the December solstice, and then the maximum is near the 2 equinoxes. And this annual semi-annual amplitude really has lots of interannual variability. And based on the satellite drag, it varies between about 30% to 250%. So this is a long-term global average mass density data derived from satellite drag data. So it's from 1967 to 2010. So you see this solar cycle variation. But if you look at each year, for example, here looking at 1976, I think. So here you can see there's an annual semi-annual variation here, and there's this annual semi-annual variation in every single year, more or less. You can see this annual semi-annual variation, and this there's also in the annual variation, annual semi-annual variation in the composition. So here I'm showing the annual variation. This is on the left top is a GUVI observation, January 2003. On the right is July 2003. So you see the global wise, and the ON2 is larger in January compared to July, and the lower figure are the TIE-GCM simulation. And so through neutral thermosphere-ionosphere coupling, so you see this annual change in the electron density. This is January of 2003. There's a lot more electron density compared to July of 2003. And now the solar cycle variation driven by 11-year solar cycle. So here looking at solar irradiance to solar spectra. So the blue is August 18, 2008, F10.7 is 68. And the red is August 18, 2002, and F10.7 is 247. So here, this is a ratio of the solar flux of these two spectra. So we see in the EUV part, the variation, the EUV at solar maximum is about 2 to 3 times of the solar minimum. And this is a model simulation of solar cycle variation of the global average mass density. Blue is minimum and the red is maximum. So at 400 kilometers, solar cycle variation of the mass density is about 1 order of magnitude. So this is the largest variation among this variation that we have talked about. And this is a typical solar cycle variation of a global average temperature. In the thermosphere here, solar minimum is about 700 K, solar maximum is more than 1100 K. And this is also in the composition. So this is a GUVI composition, 2003, and then goes through all the way to 2007. So you see that as solar activity going down, also ON2 becomes smaller and smaller. And also here, this is January. So the northern hemisphere is a winter hemisphere and the southern is the summer hemisphere. So you see that most of this solar cycle variation happens in the winter hemisphere. So we can see it more clearly if we do a zonal mean. So this is January, so northern is winter hemisphere, and this southern is a summer hemisphere. So most solar cycle variation occurs in the winter hemisphere. And the reason is because the composition is determined really by 2 factors. One is the temperature and the other is the circulation. So in the summer hemisphere, at high solar activity, you have higher temperatures that increase ON2. But in the summer hemisphere, the vertical wind is upward, and that decreases ON2. So that when you add these 2 factors together, you see very small change in ON2. But in the winter hemisphere, at solar maximum, you have higher temperature that increase ON2. In the winter hemisphere, you have downward vertical wind that also increase ON2. So you have larger increase in the ON2. So this is a model and data comparison of the solar cycle variation in global average mass density from 1996 to 2013. And the black is derived from satellite drag and the red is from TIE-GCM simulation. So we see this solar cycle variation in the global average mass density. And also each year you have annual and semi-annual variation. And this is the summary. I just leave it here. And if you have a question, please ask question.
Thank you, Liying. My alarm just went off to tell you that you should stop soon. So
yes, I will stop.
Let's see, Ryan, have you been looking at the chat?
Yes, there was one question there from Bert van den Oord. For the drag data, did you use GOCE and swarm data, or did you use other types of data?
I use CHAMP data, neutral density from CHAMP satellite.
Okay.
Okay.
Another one then just come in from Laura Hayes. Can you identify solar flare disruptions in the satellite drag data?
Satellite like that X17 flare is cause 30–40% of mass density change at 400 at CHAMP satellite altitude. Yes, so you can feel the effect. Certainly, that's a very large change.
Okay.
All right.
Another one just come in if we have time for one more, or
yeah.
And this is from Dean. Is the winter hemisphere effect in the solar cycle variation important for mission planning?
For what? I'm sorry.
For mission planning, for launching missions, is the winter hemisphere effect in the solar cycle important?
So the winter hemisphere, winter hemisphere would have a larger, more composition, so ionosphere will have, it will also have more electron density. And as for mass density, I haven't looked at the mass density. And also when I think about the mission, it would be, you would think about the mass density. Mass density would have less difference in terms of summer and the winter hemisphere, because in the winter hemisphere you have lower temperature, you have higher composition but lower temperature. But in the summer hemisphere you have a higher temperature, lower ON2. So when you put these two factors together, mass density would not have a very big difference in the summer and the winter hemisphere. So I don't think there will be much difference when you are in the winter hemisphere.
Okay, and one more just come in from Lindsay. It seemed to me that the ratio of helium-2 irradiance was a factor of 5 or 6 between solar maximum and minimum, not just a factor of 2. I think that's a comment more than a question.
I'm sorry, is that
the ratio of helium-2 irradiance between solar minimum and solar maximum? This said it looks like about a factor of 5 or 6. Can you comment on the ratio of helium-2 irradiance between solar minimum and solar maximum?
Okay, so the question is why the solar irradiance is a factor of 5 or 6 and the mass density is 1 order of magnitude? Is that the question? Is that the comments? I mean, is that the question? Yeah.
Yeah, I'm not too sure what the question was, Lindsay, or if it's.
How about we talk about that in the.
Yeah, I think we can continue that later.
Charlie can explain what he's talking about. Thank you, Liying.
Okay, I will stop share.
All right, and our next speaker seems to have disappeared from the Zoom session and isn't responding to requests. So if Christoph, if you're on, can you type something in the chat? Maybe you're logged in as a different username. I'll give you a few seconds to do that. If you're there. If you're not, then we are going to go on and hopefully come back to Christoph when he can. All right. We'll give up on Christoph for a moment and go to the next talk, Justin Deegan.